Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next episode in the Coding a 2D Game Engine in Java series. If you remember in the last tutorial, we talked about an entity component system and started getting some of our higher level stuff set up so that we can start reducing the amount of boilerplate code that we have inside of our level editor scene. In this tutorial, what we're going to be doing is offloading our VAO creation and everything in our mesh creation to a batcher. So we will be creating a render batcher, and we will be batching up to 1,000 quads or however many you want into the game, which will reduce frame rates from what could be 1 frame per second literally all the way up to 60 frames per second. So we will be learning how to do all of this, and first I'll explain exactly what batching is, and then we will go over in code and see how it all works. Okay, so let's try this and see if we can get it done. Before we begin coding, let's discuss what batching is. So in 2D games, you have the advantage of knowing that you are dealing with very simple geometry nearly all of the time. What I mean by that is you can literally represent your entire game using nothing but sprites, which are essentially just 4 vertices and 2 triangles and 1 square. Literally, that is your entire game world. Even more complicated things like this down here, this is actually just a semi-transparent sprite. And so using this fact, we can now say, instead of drawing all of this one by one, what we would typically do is say, okay, draw this one, then draw this, then draw this, then draw this, so on and so forth until you end up drawing every single one. That is very, very slow. So instead of that, what we can say is, okay, we know every single thing is going to be in the form of this, so let's batch it together. Let's make one giant mesh where everything is interconnected, and it looks something like this, and we'll support up to 1,000 squares per mesh. And then we do, okay, now we can fit all of this into one draw call, and we end up drawing one. I did some performance testing, and 10,000 squares without batching gives you 1 FPS. 10,000 squares with batching gives you 60 FPS. So this is essential if you want a functional game. It really does help things out a lot, and you don't have to do much to check and see that it does a lot. But how do you do this? How does batching work? Well, like I said, we know that everything can be represented by squares, by these quads, which we know from previous tutorials is just 2 triangles. Well, we also know that if we order the vertices in such a way, v0, 1, 2, 3, then we can order them into, we can just stuff them into one big array, right? And then we're going to upload this to the GPU anyways. Well, let's say, and this is at the actual format we're going to use, we want to have position X, position Y, and then R, G, B, A, so the color. So we'll have position for each vertex and color. So this would be like the position here in the world, and that's what we want for every single vertex. Then we know that the way we would order this to draw it correctly for the elements, so this is the triangle order, we would say, well, we need to do it in counterclockwise order, so let's do 3, 2, 0. We do this vertex, and this vertex. That's the first triangle. Then 0, 2, 1, which would be this vertex, and this vertex. Second triangle, and it's in counterclockwise order, which means it will show up correctly. Well, let's say we have a second sprite that we stuff into this vertex array. What do we do then? Well, as long as we're stuffing it in this order, v0, 1, 2, 3, then we do 4, 5, 6, 7, the same exact order. We know it's going to go 7, 6, 4. We just do the same thing we did last time. And 4, 6, 5, which is just this, then this, then this. And if you notice, this is the same exact thing as this, except with 4 added to every single element. So what this tells me is that these elements you can generate automatically, which we will do, and you don't have to worry about them ever changing, whereas these vertices could potentially change. If your sprite is Mario, you know that the X and the Y are going to change quite a bit, and if we had a texture in here, the texture coordinates would change a bit too, because he's constantly being animated. So what that tells me is we can generate this one once, upload it to the GPU, never have to change it, and we know exactly the format it's going to take, because as long as we stuff in the vertices in the correct order, it will always take on this type of pattern. And then with our vertices, we can just upload once with our initial set of vertices. And then every time some of them change, we can go into the array, specifically change that vertex, and then re-upload that specific portion, which is the whole essence of batching. So this is the format we're using. Now, I think you guys can probably do most of this on yourself. If you want to give it a try, this is exactly what we will be needing. We will have a couple other helper functions and stuff, but this is the gist of the most important stuff. We will be creating a renderer class, and this renderer class will have two main functions: add game object, which will take in an object, and then render. So this will also contain a list of render batches, and render batches are this next class that we will be creating. And a render batch is where all the heavy lifting is going to happen. It will have a start method. This is where we create the VAO, the VBO, and the EBO. So all that work we're doing in the level editor scene will be stuffed into here. We will have an add sprite function, which takes in a sprite render and then adds that sprite to its own list of sprites, which we have right here. And that way it can figure out if any of them are changing or not. Then it has an int array, generate indices, which we said up here is always going to be the same. So we can generate those once, these guys, and we know that's never going to change. Then you have your render function, which gets called by this render function when it's going through all of its render batches. And lastly, I have this helper function, load vertex properties int index, where it would basically say, okay, so say you want to load vertex 0's properties, you would say load vertex, you would say load 0. And then it would go and it would create 4 of these. So x0, x1, x2, x3. Because it would be loading in every single one of these vertices, because this is one sprite. This is one quad. And then it has a shader for rendering, and it has a float array which contains all the vertices, and it has a VAO ID and a VBO ID. So let's actually try and code this and see if we can get this all figured out now. So before we begin doing the render stuff, we have to do a couple more things that are going to be essential for that render. One of them is creating the transform for our game object. So we'll create a new class in here, call it transform. And transform will very simply contain a couple of public variables. So we'll have a 2f for its position, and we will have a public vector 2f for the scale. And then we'll take in a couple of different methods that can initialize it. So we'll have one that just says this dot position equals a empty. So this will initialize it to 0, and this dot scale equals this, which is just empty again. And actually, let's pull this out into an init function, because this always simplifies things a little bit more. So we'll say position and vector 2f scale. This is what I typically do if I have a function that I want to overload. I'll have one main function, and then I will have several that just call this main function. So we'll just say this dot position equals position, and this dot scale equals scale. And then inside here, we'll say init new vector 2f, new vector 2f. Then we can give it public transform vector 2f position. If they just want to supply the position, then we'll copy this and we will pass in position. And then we will do one more that takes in position and scale. So we'll say public transform vector 2f position and scale. And then we'll just say init position and scale. All right, there we go. So now we have our transform, which should allow us to publicly access these variables, which will be very helpful. Next, let's actually add this to our game object. So we'll go up here and we will say public transform. And this will be like one of the only public variables we have, which you'll see why in a minute too. We'll just say this dot transform equals new transform in here. And then we'll say public game object string name and transform. Then we'll just copy this and do it here. And we could do the same thing we just did back there, creating an init function and stuff, which I would suggest, but I'm trying to get through these things kind of fast. Then let's go up to our sprite render. Since we will be using this, let's delete that code we had before. We no longer need to know about this stuff or this stuff. And then inside of here, what we're going to do is we're going to say vector 4f color, because we are going to be taking in a color now. And we will have a vector 4f here, which is the color, and we'll just say this dot color equals color. And since this is going to be private, we will need a way to get that color. So we will go down here and add in a public, not private, vector4f get color. And this will just return that color. So this is all stuff that's not super complicated, but it's stuff that you just need to get done. Okay, last couple things that we have to get out of the way. Let's go to our window and create a getScene function. This will also be very useful because there are many times that you just want to get whatever scene you're operating on. So we'll say public static scene getScene return get.current scene. Very simple, but it will be helpful in a ton of situations. And then the last thing that we're going to do is go to our scene, and we are going to add a camera function that just gets whatever the camera is. So we'll say public camera return this .camera. All right, so I promise that's it. Now we can start going on with the actual RenderBatch stuff. This was all important though, just that we can get it all done very easily. So let's go into our render now. We'll create a new class and we will call this RenderBatch. So like you saw before, this is what is going to contain most of the heavy lifting, and it's going to be doing pretty much the majority of the stuff we need. So what I like to do inside of these batches is define the layout of my vertex. So we can't really create these things called structs, which are very helpful in C++, which allow us to do this. So I like to just define it up here so I know exactly what it should look like. And in our case, we're going to have a position and then a color, which will just look like this. We will have position, which is 2, and then 4 colors, 4 floats for colors. Then, just like we were doing inside of our level editor scene, we're going to create these final ints called basically the size and everything, so that we just know the size, the offset, and then the vertex size and the vertex size in bytes. Just like we did, if we go into the level editor scene, we did all that right here. And it's the same concept we're doing, except we're just going to do it once because we know exactly what the layout is going to be and we never have to redo that. So we'll say the pose size, there's 2 of them. Private final int color size, well, there's 4 colors. And then we'll say private final int pose offset. Well, that's 0. The position starts at offset 0. Private final int color offset equals pose offset plus pose size times float dot bytes. So remember, the offset is in bytes, and we know that the offset for color starts here, which is 2 plus however big a float is. So the pose size times bytes, which gives us the correct offset for the color. Then we'll say private final int vertex size. The total size of our vertex contains 6 floats. And we will finally do one more, the vertex size in bytes, which is just the vertex size times float dot bytes. And that will just allow us to pass everything in very easily, and we'll be able to read it and know exactly what's happening. We'll need a couple more things. Like I said, we will need the sprite render, and we'll just create an array of sprites because we'll know exactly how many sprites one batch should take in. Of int number sprites. This is how many sprites we currently have inside of our array. Of private boolean has room. Do we have enough room or not? Private float are vertices. So this will actually contain all of this vertex information literally just stuffed inside of this giant array. Then we'll say private int VBOID, and we are going to create the EBOID inside of the start method, which we will do in a second. And we'll need a max batch size and a shader. Okay, I know this seems like a lot of stuff, but I promise it's all necessary and it will all make sense as we go through and sort of pull stuff out and redo everything. Now, when you create a render batch, what we want to do is pass in a max batch size, which will tell us how many quads we want this batch to be able to hold. So that way we just know exactly how much we're going to use. Let's create our shader in here too. We'll just say shader equals the new shader, assets/shaders/default.glsl. So we'll just pass in the default shader we've been using. Let's say shader.compile. Then we will say this.sprite equals a new sprite render. How many will we hold? Well, we will hold max batch size, of course, right? Because that's the maximum amount of sprites that we will be able to hold inside of this sprite renderer. So we just create an array that big. Now we'll say this dot max batch size equals the max batch size. Then we need something else. How many floats will we need for our vertices? Well, we know that each sprite will contain 4 vertices because they are one quad, and we know that each vertex, each vertex, has 6 floats, which is stored in this vertex size. So using that information, we know that we will need max batch size times 4 times vertex size, because we have 4 vertices per quad, and then we have max batch size sprites possible, and we have vertex size floats in one vertex. So that should give us the correct amount of vertices that we can hold. Then we'll say this dot number sprites equals 0. We don't currently have any, and this dot has room equals true. We definitely have room since we have 0 sprites contained inside of this. Next function we want to do is create the start function. So this is where we will create all the data on the GPU. So we're going to allocate room on the GPU and say, hey, this is where we're going to be working with. Please give us enough space, and it will do that. So first thing we're going to do is generate and bind a vertex array object. Just like we did in the level editor scene, we'll say VAO ID equals GLGen vertex arrays. And what this does is it generates a vertex array object ID for us that we can use. And then we will say, give us or bind that array object because we will be using it. So we bind it to our GPU. Then we'll say allocate space for the vertices. We kind of have a quagmire here, right? We want to start it, but we don't have any sprites. We know how much space we're going to need though, which is all the GPU needs. As long as you know exactly how much space you're going to need, it can allocate that space for you, and then you can use it when you're ready. So what we will say is VBOID equals GLGenBuffers, and let's import that. So we generate that buffer ID, then we'll say bind the buffer. So this is going to be an array buffer, and we're passing in the VBOID. Import those. Then we will say GLBuffer data. So this is the one we used when we actually had data, but we don't now. And if you notice up here, it says we can use this one, which says it takes in a target, the size, and whatever your usage is. So I'm going to get this out of the way. We can tell it, okay, we know that we are going to need vertices.length floats times float.bytes. It needs it in bytes. So we know we need this many floats at least, and we know the size of one float in bytes is this. And so that is what we pass it, and it will allocate that space for us. And then this is the last thing that may be different. Instead of static draw, we're going to say dynamic draw, because remember, our vertices can change. So we need to tell OpenGL, hey, we are going to be changing this in the future. Make sure you put it in a place where we can read and write to pretty efficiently. And that's what that does for us. Next, we're going to create and upload the indices buffer. So we're going to say int EBOID equals GLGenBuffers. And remember, this is just so that we can reduce vertex duplication by indexing when we are drawing our quads. Just like I showed you with those triangles, we had V0, V1, V2, all that stuff. Then we'll say int indices equals generate indices. Remember, the indices are never going to change, so we'll be able to generate them, which we will do in a minute. Let's finish uploading our hypothetical indices to the GPU first, though. So we'll say bind element array buffer, and then we will say EBOID is the ID that we are binding to. Then we will say buffer data, GL element array buffer, and the data we're buffering is our indices. And we can say that this is GL static draw. We know we are never going to be changing the indices because they will always remain the same. So we can tell GL, you can put those wherever you want, whatever's best for you. And it doesn't have to worry about us writing into it. We just need to read from it. So that's what we do. Then we will enable the buffer attribute pointers, which are basically just telling it how our vertex is laid out. So vertex attribute pointer 0 is going to be our position size. It's going to be a float, and let's see what else it takes in. And normalized is false. The stride will be our vertex size in bytes, and the pointer will be pose offset. So that's our offset for us. Then we can say GL enable vertex attrib array 0. So we will enable that vertex attribute right after we do that. So just so you can see, that's what we're doing. Then we're going to be doing basically the same thing except for our color now. So we'll say GL vertex attribute pointer 1, and this is going to be our color size. This is going to be a GL float also. It's not normalized, so false. And the stride is going to be vertex size in bytes again. And the buffer is going to be color offset, or the pointer, not the buffer. And then we'll say GL enable vertex attrib array. No, not array, pointer. Attrib pointer 1. And what we're doing here is literally the same thing that we talked about. Up here, we want our vertex to look like this. And so now we're telling the GPU, hey, we want our vertex to look like that right here. That's what we're doing. Now let's create this generate indices function, which is actually pretty simple because, like I said, they follow a very strict pattern, which makes it easier for us when we're generating them, right? So we'll create this function, private int generate indices. And we're going to say, okay, we have 6 indices per quad because we have 3 indices per triangle. So that lets us know how big the array has to be. So we'll say elements equals a new int, and we'll say 6 times the max batch size. We can have up to 6 indices per sprite, and we can have this many sprites. So we will allocate enough space for that. Then we'll say for int I equals 0 until I is less than max batch size, I plus plus. And what we're going to do is we're going to create another helper functions, load element indices. We will pass in our elements and the index we are currently at. So now what we will do to load the element indices, we'll say private void load element indices, which will take in our int array elements and our index. And this will modify this array inside here, which is why we don't have to return anything. When we pass this array to here, it's passing a reference, which means whatever we do to it in here will actually change it in here as well. So what we need to do is we need to find a couple of offsets. So we're going to say offset array index equals 6 times index, and int offset equals 4 times index. And what this basically means is, remember I was saying that we have our triangles, and they look like 3, 2, 0, 0, 2, 1 for the first quad. The next quad is 7, 6, 4, 4, 6, 5. Well, we have a couple offsets we need. So if we're looking at quad 1, which would be this one, we know that the offset in the array is 0, right? So we would do 6 times index. So this is the 0th element, which would give us 0. Then we need the offset for the start of this number. What is this first number? Well, that's 0, so 4 times index. Then it makes more sense if we do this one. 6 times index, this is the first one, so we would get 6, which means that would be 1, 2, 3, 4, 5, 6, 7. If we start from 0, 6, which is this index, then the offset is 4 times 1, which is 4, which is the number we need right here. So that's basically all these mean. You can leave that comment in there if it helps you out when you're thinking about it. So we'll say creating the first triangle, triangle 1, which is 3, 2, 0, and then we need 0, 2, 1, which is triangle 2, will be elements offset array equals offset plus 3 offset array index. Sorry about that. Then we'll say elements offset array index plus 1 equals offset plus 2. Elements offset array index plus 2 equals offset plus 0. And you can see what I'm doing. 3, 2, 0, 3, 2, 0. And we're just going up 0, 1, 2, 0, 1, 2, the index into this array, and then the numbers we want at that position. So literally just taking that pattern and copying it multiple times. Then we'll copy those and do one more, and then we'll say this is going to be 3, 4, and 5 for triangle 2, and the pattern is 0, then 2, then 1 for triangle 2. Then we can be done. So this will load the element indices for whatever quad we are currently working on. So now we have that done, we can say after we finish loading every single quad, we will just return the elements, which will give it to him, and then he can actually bind it and upload those vertices. That should be the only time we ever have to call that. Now, let's assume we have data inside of our vertices. Let's create a render function because this is the next kind of easy step. I'm going to say for now, for now, we will rebuffer all data every frame. Remember how I was saying that we could change it so that we could rebuffer only a sub portion of the data? If only one vertex changes, we only have to change that vertex. Well, we can, but it's a little bit hard to do. So we will save that for a future tutorial. For now, what we'll say is we're just going to rebuffer the whole vertex array every single frame, which is still faster than one draw call per item. So we'll say bind the VBO ID. This is why we held on to that ID. And we're going to say buffer subdata, even though technically we're buffering the whole thing. GL array buffer. Now let's get rid of this thing so that we can actually see. And it asks for an offset, which is 0. Then it asks for the data, which is our vertices. And then it asks for nothing else. That's it. So basically what this does is it says, okay, I'm going to buffer some data into this VBO that you guys gave me, this buffer. And we want to buffer our vertices starting from 0. And then it will just upload all the vertices starting from 0. So that should be good for that. Then we want to make sure we use our shader. If we go into our level editor scene, we are basically doing everything we did inside of this update function right here. We say upload, blah, 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 use the shader, do all that stuff. Except now we're just moving it in to our render batch. So we'll say shader.use. Then we'll say shader.upload mat for F. This is going to be our U projection, just like in the level editor scene. And we'll say window.getScene.getCamera, or just camera.getProjectionMatrix. So that's why we created those helper functions. Very useful now. Then we'll say upload another mat4f. This is going to be our U view. And we're going to say this is the window.getScene.camera.getViewMatrix. And that should be good. That's all we need. Then we'll say bind the vertex array, our VAO ID, which is the VAO for this big batch. Then we'll say GL enable vertex attrib array 0, duplicate that. We also want to enable 1. Then we will draw the elements, which is just GL triangles like we did in the level editor scene. And we will say we want to do this dot number sprites times 6 indices per quad. And we have number sprites quads that we want to draw. That's how many sprites we have. And our type is unsigned int. And we will say 0 for our offset, which is the indices. I believe that's offset. I'm not actually sure what this one does, but yeah. Okay, we're good. So we draw the elements. Then we want to disable everything. So we'll say GL disable vertex attrib array 0. Duplicate that 1. We want to say GL bind vertex array 0, unbind everything, and shader.detach. So we just reverse everything we just did. We said use, bind. Now we're saying disbind, unbind, detach, everything. And that should draw whatever's in our vertex buffer. Last thing we have to worry about. We have all the data and stuff, but we don't really have any way to get a sprite into this vertex array, right? We're never placing any data into this VBO. I mean, we are here, but we're never placing it into our local copy, this thing. So the vertices are always just a bunch of zeros. We want to fix that. So we will create another function, which is going to be add sprite. And this will allow us to add data to that array. So we'll say public void add sprite, and this will take in a sprite renderer, SPR. We'll just call it that. So first thing we're going to have to say is get the index and add the render object, which in this case is a sprite render. So index is basically where do we want to put this, and we want to put it at the end of our current array. So if our array currently has 5 sprites, it would be like 0, 1, 2, 3, 4, 5. The 5 sprites would be up to here. So then we would say, okay, well, the length is 5, so that will give us the next index in the array that we need, which is basically why we say the number of sprites is what we want. Then we'll say this dot sprites index equals the sprite, so we put it into that array, and we'll say this dot number sprites plus plus. So then we increment it so that the next time we add one, it will be in the next slot. Then we want to add the properties to local vertices array. So we want to add all those float properties. So we'll just say we're going to call some magical function load vertex properties index, which we'll create in just a moment. And then last thing we want to say is if the number of sprites is greater than or equal to this dot max match size, then this dot has room equals false. Just so that we make sure we're updating that. If we have filled up our array, we want to make sure that we tell them we have no more room inside of this batch. So how does this magical load vertex properties function work? Well, let's go below our render function. We will create it right here. We'll say private void load vertex properties, which just takes in an index. Well, this is basically, we need to create 4 vertices per quad, and this is where we're going to do it. So first of all, we're going to say sprite render sprite, sprite equals this dot sprites index. So we're grabbing that sprite we just created and passed in. Now we want to say find the offset within array. There's 4 vertices per sprite. So the offset within the array is going to be index times 4 because there's 4 vertices per sprite. So equals index times 4 times vertex size because there's this many floats per vertex, which is in this case 6. So basically, remember we have float, float, and then we have float, float. So we have the position, then the color, and we know that's this size. And then we know we have 4 of these per sprite. So then the total offset, wherever we are inside of this array, this will be like the next one, would be the index times 4 times vertex size, which will give us the appropriate number. So that's the offset. Then we'll say vector 4f, what's the color we have for this sprite? Well, that's just sprite.getColor. So that one's easy too. Now this is the kind of confusing part, but we'll go through it step by step. We want to add the 4 vertices with the appropriate properties. And you could go and do this manually, but we could just loop over and do this a little bit simpler. So what we will do is we'll say float x add equals 1.0f, float y add equals 1.0f, and then we'll say for int I equals 0, I is less than 4, I plus plus. So we know that our vertices are going to be, we're going to have 1, 2, 3, 4 per quad, right? We have top right, bottom left, top left. And what I'm going to do is I'm going to say, okay, we're positioning everything according to, I think, either the bottom left or the top left corner. I think it's the bottom left corners we're positioning everything from. And the way we control that is we're saying we're going to add the top right, 1.0, 1.0. Then we're going to add the bottom right, which we'll say if I equals 1, then y add equals 0.0f. So on the first, once we add the top, then we will go to this one. Then we're going to add the bottom left. So then we'll say else if I equals 2, x add equals 0.0f. Then we're going to add the top left, which we're going to say else if I equals 3, y add equals 1.0f. And basically we're just going to use these numbers to figure out exactly how far, because if we use 1 and 0, then we can say, okay, well this is going to be from wherever we're positioning it, it's going to be the width, so whatever that is, plus the position. So the width times x add plus the position, and that will give us the appropriate coordinates. If that doesn't make sense, please leave a comment, and I may post a follow-up video because I have to go through this kind of fast. So we're going to say load position first. We're going to say vertices offset equals sprite.gameObject.transform.position.x plus x add times the sprites gameObject.transform scale.x. Whoops, scale.x. And this will give us the correct offset no matter what, because x add will be 0 or 1 depending on which one we're actually adding. Then I'm going to duplicate that, and we're going to say offset plus 1, and we're going to do the same thing except for y, and we're going to use y add, and we're going to use scale.y. And that will make sure that we order the vertices in the correct order. Then we're going to load the color in. So then we're going to say load color, which is going to be vertices offset plus 2 equals color.x. Duplicate that a few times. We'll say y, this is z, and this is w. And then we'll say going up 3, 4, 5, okay? And then lastly, we will say offset plus equals vertex size. What this does is, remember we said we wanted x, y, then RGBA. That's exactly what we're doing for every vertex. And then for every quad, we're adding 4 of these. That's why we're looping, and we're incrementing x add and y add so that we get the appropriate vertex position. It's a lot, but it should work, and we still have quite a bit to do. So let's get that done real quick. Now let's go into our render real quick, and we're going to create a new class. This is going to be called render, which will actually render all the objects. and we're going to give it private final int max batch size. I'm going to say is 1,000. That should be good. And then we're going to need a list of render batches, and we're going to call this batches. Then we're going to say public render. When we create it, we'll just say this dot batches equals a new array list. So this is what's going to be in charge of submitting it to the appropriate batch and everything. So we'll say public void add. This will take in a game object go. And what we're going to do is we're going to say sprite render spr equals go.getComponent sprite render dot class. And we'll say if spr does not equal null. So if this game object actually does have one, we'll add it to our render. So then we'll say add spr. We'll create one more function down here, private void add. This will take in a sprite render spr ite sprite. And then what we're going to do is we're going to loop through any current batches we have. We're going to say added equals false. We have not added it yet. We're going to say for RenderBatch batch in our batches. So in the batches that we have, if the batch dot has room, which we will create in just a second, then we'll say batch dot add sprite, and we will add in this sprite. And we'll say added equals true and break out of that loop. So if it has room, we can add it. If we get to the end and we did not have any room, we were not able to add it, then we'll say we'll create a new batch. So we'll say render batch new batch equals a new render batch, which takes in the max batch size, which we conveniently have at the top of this class. Then we'll say new batch.start. We will start it immediately, and we'll add it to our list of batches. So we'll say batches.add this new batch. And finally, we will add in this sprite that we wanted to add. And that will actually add a sprite to our batches successfully. Let's go back into our render batch, create that function real quick. We already have has room inside of here, so we'll just say private boolean has room. Return this dot has room. Very simple. Make sure to make this public. We don't want that private because we do want outside classes to be able to use it. Lastly, we want to create our render function, which is just going to go through each of the render batches. Render batch in batches, and it's just going to say batch.render. So this one is nice and easy. It's pretty straightforward. We just add it to an available batch, and then we just create a new batch if we need to, and then we render. Not too much going on here. Now we want to actually add this to our scene so that we can add some stuff and see if it all works out right. So at the top of our scene class, we will go up here. We'll say private renderer, which is just that class we just created. We'll import that. And then inside of the start method, we will say this.render.add go. So this will be called at the beginning of the scene when the scene is being started, and then it'll loop through all the game objects and start them, and then we can add it to the render. If the game is running, we want to make sure that we also add it. So we'll say this.render.add go. So if we are adding a new game object to the scene while the game is running, we can add the game object to the render right down here. That should take care of adding the game object to our render now. Finally, we can go into our level editor scene and clean this up. So I'm going to go through here, delete all of this, except for that game object loop. Like I said, that's the only thing we want to keep. Delete all of this. And I know this might scare some of you, but it's fine because we offloaded all of this. Delete all of that stuff. This is so nice, much cleaner for our level editor scene. We can even go up here, delete all the imports that we don't need anymore. Inside of init, let's create something to test this batch render that will render 10,000 cubes, not cubes, squares. So inside of init, we'll say, whoops, this dot camera equals a new camera because we have to initialize that. New vector 2f00, that's fine. Int x offset equals 10, int y offset equals 10. This is, we want a buffer of 10 for padding or whatever. Float, total width, this is going to be the total width of the square. We're going to say is 600 minus x offset times 2. Float, total height equals float 300 minus y offset times 2. Don't worry if you don't understand what I'm doing. I didn't really understand what I was doing either. I just sort of messed with things till it worked. And it's fine because this is just test code, so it doesn't really matter. And we're going to say size y equals total height over 100.0f. Then we're going to loop through and we're going to say int x equals 0 until x is less than 100, x plus plus. for int y equals 0 until y is less than 100, y plus plus. So we're going to create 10,000 objects, 100 times 100, 10,000, I think. And then we're going to say float expose equals x offset plus x times size x. This is the position inside of our game world. And we're going to say y pose equals y offset plus y times size y. Then we're just going to say game object go, create a new game object. And we're going to say this is obj plus x plus y with a new transform, new vector 2f. We're going to say x pose, y pose for the position, and then new vector 2f for the scale. We're going to say size x, size y. So we'll just create a new game object like that. Make sure you don't have any syntax errors. And then we will go.add component, new sprite render. We're going to say new vector 4f. We're going to say x pose over total width, y pose over total height, 1 and 1. So that's the color we're going to use, which is going to be based on its position. So we should get a nice gradient. And then we'll say this.add game object to scene, go. And that should be it. We should be good. And then finally, we will want to render it. So we'll say this.render. And we need to make that protected inside of our scene. So let's go up here, change this to protected. And we should be good. So let's hit run and hopefully we get the square, but we're going to get an error. So let's see what's going on here. And it's saying render is null. Do we ever add? We don't ever add this, I don't think. So we'll just say up here equals a new render, and that takes in no parameters just to initialize that inside of your scene class. There we go. We get a picture. Right now it's black. Why the heck is it black? Well, remember our default.glsl, we did a couple things, so this isn't going to work properly. Remove layout location equals 2 in here, and we will remove f text chords. Take out f text chords here. This should all be good though. We'll take out time and the sampler, and we'll take out f chords here. And instead of doing this, we'll just say color equals f color. So we were sampling from textures before, which is why it was black. But now if we use the color passed in, we get this nice gradient, which is awesome. Last thing you can do just to see and know for yourself that this really is doing a lot. If we go back into our level editor scene, you can print out the FPS just by saying system.out.println FPS and then doing 1.0f over dt. That should give us the frames per second. So if we do that and we run, we see we're running at 60 frames per second on my machine. You may be running at something different depending on your refresh rate of your monitor. But if we change our batch size, let's go into our render and let's change our batch size to just 10 even, okay? This is going to slow it down dramatically because there's 10,000 triangles. Actually, still runs pretty good. Well, let's bring it down to 1 and then you'll see what I mean. Okay, so now it's starting to take a minute for my computer and now I'm getting 2 frames per second because it's doing 10,000 draw calls per frame, which just is not good. So just by increasing this to 1,000 quads per batch, we increase our frame rate from what would have been 1 frame per second if we had been drawing 1 square at a time to 60 frames per second. This helps tremendously. This is super important. Yeah, this is why we needed batching. It actually does create a significant performance improvement that we can see immediately. There are problems with our batching routine. There are things that we will have to fix along the way, but this is the gist of it, and we will add the new things as we go along, things like textures and stuff like that. I hope you guys like this. If you did, please hit like and subscribe. In the next tutorial, we will probably be going over asset pool because that is something that we desperately need right now. I'll see you guys in the next tutorial.